Welcome back, time travelers from the future. I'm Steve Brunton, and I'm going to tell you about machine learning for fluid mechanics. Now, I am calling you time travelers because time travels so very fast when you're talking about machine learning. And between the time I make this video and the time you watch this video, there may indeed be significant changes to the state of the art. I actually gave a version of this lecture no more than 3 or 4 months ago, and then found this amazing kind of rendering by Petros Vrelis of Starry Night using this kind of flow mapping visualization. So lots of cool things I'm going to talk about in machine learning for fluid mechanics. In this video, I'm going to focus in particular on how we use machine learning to model and to control complex, unsteady, high-dimensional flow fields. So I'm pretty excited. This is a topic very near and dear to my heart. All right, and we've already talked about before how kind of you can in broad brushstrokes summarize machine learning as optimization based on data, and in particular, that optimization is often building models from data, and you can use those models to predict, to estimate, and to control your fluid system. And here's just a small illustration of some of the many applications of fluid flow in our daily lives in significant industrial and societal systems: transportation, energy, defense, health. This is a diagram from a review paper I wrote with Bernd Nowak a few years back. And again, just to remind you, most of our fluid dynamics tasks here in blue can be written as these really hard optimization problems in pink. And today I'm going to focus in particular on modeling, control, and closure problems, how to pose them as optimization problems, and then how we're currently using machine learning to start solving these problems. And I'm going to point out at the outset, there is so much good work on this. There are hundreds of groups from around the world tirelessly working on implementing machine learning to solve increasingly hard problems in engineering fluid mechanics. A lot of what I'm going to tell you about is from my group and the groups of my close colleagues and collaborators, but I do want to kind of let you know that this is just a very, very shallow topical treatment of this really rich and interesting subject. Okay, so let's jump in. And a lot of this is going to follow kind of some of this material outlined in this review paper with myself, Bernd Nowak, and Petros Koumoutsakis from 2020. And we're going to talk about how to use optimization for modeling and control in fluids. Good. All right, so I've been kind of bringing this up over and over and over again, this idea that patterns exist in the data, and that's why we think we can model and predict and control these fluid systems. And pattern extraction, kind of the theory of pattern identification and extraction, has a rich history, and that's actually a lot of the machine learning, the modern machine learning algorithms grew out of kind of pattern extraction theory. Okay, so we're going to use these patterns in flow fields to model, to predict, and to control kind of the future evolution of these flow fields. And I love this picture. This is from a review paper by Sam Tyra and co-authors in the AIAA journal, where he shows this kind of correspondence between a very complex geophysical flow. This is the flow over Rishiri Island in Japan. And although this is an extremely complex flow, I mean, I don't know how large a kilometer is in this picture, but I mean, this is on Earth scale, right? This is a mountain here. But the flow patterns actually, are very close to this very, very simple toy problem, flow problem that we've all been working with for decades. Okay, and so these patterns allow us to simplify problems. But where does this complexity come from in the first place? So that's where I'm going to start with this lecture. Okay, and the complexity I like to think of, this is the Navier-Stokes equation for an incompressible fluid, and this is a non-dimensional form. The complexity is really entering here in the Reynolds number term, this 1 over Reynolds number. So as your flow becomes either bigger or faster, roughly speaking, this Reynolds number increases, and the higher the Reynolds number is, the smaller the effect of viscosity, or rather viscosity acts on smaller scales, and you get more and more and more turbulent, complex, multi-scale behavior in your flow solution. Generally, I'm painting with really broad brushstrokes here. But the Reynolds number is kind of this parameter that modulates the complexity of your flow. And this is a great diagram I grabbed from the Feynman Lectures, Volume 2, where you have these beautiful hand-drawn pictures of this flow past a cylinder. As you increase the Reynolds number, you see this increasing flow complexity. So you have this very simple kind of steady laminar solution here. This is what like tiny, tiny, tiny microscopic organisms would look like, their flow field. And as you increase the Reynolds number, you start to see these wake structures, this Kármán vortex street. Then it becomes turbulent, like the flow over Richieri Island. And then eventually it becomes turbulent and kind of reattaches. So you get this incredible range of complexity just by varying this one parameter, the Reynolds number. And it's interesting, you can also look at the drag on each of these cylinders at each of these Reynolds numbers. So the y-axis here is drag coefficient. The x-axis is the Reynolds number. And you see that you get this incredible range of drag values as you increase the Reynolds number from very, very low to very, very high. Okay, so if you drop a ball from the Leaning Tower of Pisa, it doesn't actually accelerate at a constant rate given by the gravitational constant, because you have all of these kind of various fluid forcing that's also impeding or fighting the downward acceleration of that ball. So really interesting. Complexity enters through this Reynolds number, and you get this massive range of scales as you crank up that Reynolds number. Okay, good. Now, oftentimes we don't care about resolving all of those many, many scales in a fluid system. Oftentimes what we really care about are the big, dominant energy-containing structures, coherent structures in the flow. So, you know, if you think about that picture of the clouds past Richieri Island, maybe I only care about those big vortical structures and I don't care about all of the little turbulent structures on top. Okay, and so this is a picture that anyone in fluids is you know, very familiar with, the Kolmogorov turbulent energy cascade. And what we have here on a log-log plot is the amount of energy in each of these spatial wave numbers, from low spatial wave number, big low frequency vortices, all the way up to very, very high spatial wave number, teeny tiny little vortices. And again, flows are characterized by this multi-scale in space and time behavior. So if I look at the flow around a submarine or a jumbo jet, I'm going to have big flow structures that are on the length scale of the object itself. And then I'm going to have medium and smaller, eventually getting teeny tiny little flow structures. Maybe they're millimeter length scales. And so you get this massive range of spatial scales, maybe 10 orders of magnitude for some of the largest industrial flows at scale. But again, I don't necessarily care about every single degree of freedom in this fluid. I might just care about the big coherent structures that I need to care about for lift and drag and noise and things like that. Okay? Actually, noise is a really hard one. That one's not as easy. Lift and drag. And so this is the basis of a huge effort in fluids called closure modeling. And closure modeling basically tries to get low-order models, simple models that describe the big stuff, the big energy-containing stuff, while still somehow accounting for at least the statistical effect or the average effect of the small scales. Okay, and I'm again, broad brushstrokes here, but that's more or less what we're trying to do in closure modeling. And so mathematically, the way I can write this, and this is kind of just a toy system that I've written down for my own understanding of this, is that maybe I care about the first few big energy-containing structures in X1 and X2. These are variables that describe kind of those big structures. And then maybe I have all of these higher order little teeny tiny vortices that are described by X3, X4, X5, and so on and so forth. But this gives you a big coupled system of differential equations. The Navier-Stokes equations is a big coupled system of differential equations if you discretize or you project onto modes or something like that. And so it's really hard to untangle the effect of these small scales on the big scale. And that's the goal of closure modeling. So we can't resolve all scales. We don't want to resolve all scales. It's too expensive. It takes supercomputers, and we still can't resolve the most industrially relevant flows we care about today. They're too slow for optimization and for control. So we need low-order models that aren't completely accurate, but are good enough for some of our high-level objectives of design and control. Okay? And so the goal here is essentially to get a proxy for these high frequency structures here and how they act on the low frequency structures here, given by this expression. So we want some representation of the high frequency structures in terms of the low frequency structures, which we can then substitute back into this first equation, which gives us this closure model. So that kind of boxed equation is only in terms of the big low frequency dominant coherent structures. And it approximates the effect of these high frequency structures here. Now, this is one type of closure modeling. There's many types of closure modeling. There's large eddy simulation. There's Reynolds average Navier-Stokes. There's unsteady Reynolds average Navier-Stokes, URANs, all kinds of approaches to this closure modeling problem. This is just kind of how I think about it in terms of differential equations and dynamical systems, because that's how I think about things. So we want this simplified equation, okay? And that's really, really hard to get. So can we start building this with machine learning, with a wealth of data? Can we start building these proxy models for how the high frequency stuff would depend on the low frequency stuff, or kind of averaging the effect of the high frequency stuff in this low frequency equation? Can we start getting proxy models from machine learning? Because we have so much data from turbulence. We have massive turbulence simulations. There is the Johns Hopkins turbulence database. Stanford has a big turbulence database. Many researchers around the world are generating just server rooms full of hard drives full of flow simulation data of turbulent flows. Can we learn from that wealth of data to start figuring out these closure models? Okay, there is a really, really nice paper that summarizes some of these modern efforts, turbulence modeling in the age of data, by Durasamy, Yaccarino, and Shao. And in this paper, they outline some of the leading methods people are using to tackle this closure modeling problem with data and with machine learning. So if you want to dig into this and make progress on this extremely important field of research, you've got to read this paper. This is the entry point. And on the right, I have some of my favorite papers that are kind of research papers on this closure modeling problem. You have a lot that are dealing with Reynolds averaged Navier-Stokes equations, which is kind of a time averaged equation. And then on the bottom, you're starting to see people apply this to large eddy simulations. Okay, and this is a tiny fraction of the wealth of good work on closure modeling. And one of my absolute favorite models out there today is this RANS closure model from Ling, Kurzowski, and Templeton in a 2016 JFM paper. And what I like about this paper, and I'm going to, I guess, wax philosophical for a minute here. Whenever you want to apply machine learning to a problem in fluid mechanics or physical science or engineering, I think there are kind of two approaches. One is to just build a deep neural network, throw in your data, cross-validate, and get some results, and write a paper. And the other approach I like much better. This is what kind of Ling et al. Are doing here, which is to somehow guide the learning process with some partial physical knowledge, to constrain your learning algorithm, your machine learning algorithm, in this case a neural network, with partial knowledge of the physics. And so what they were able to do is modify their deep learning structure to include this kind of last tensor input layer, which allows them to embed known invariants and symmetries in that should be in any closure model. And this is, I think, a really important point, is that they actually went back in the literature well before kind of the deep learning literature, back to the 70s, and essentially found this early result where researchers wrote down the Navier-Stokes equations, and then made a bunch of statements of things that were absolutely true until they hit a mathematical wall. And that, at the time, in the 70s, that mathematical wall, they just couldn't get around it. They couldn't solve that problem with the tools of the era. And what Ling et al. Did was they took off where that excellent paper from the 70s left off, and then they started using better mathematical tools like these constrained deep neural networks to start getting these representations and working further. So I highly recommend you do this. Go back to the 60s, go back to the 70s, find these classical papers and figure out, because they were so brilliant back then, they didn't have the tools we have. They couldn't just crank through a deep neural network. They had to really think deeply about the physics of the problem. And so if you can go through these papers and find where kind of they set up this problem, and where they get stuck because of limited tools of the era, you might be able to write a new classic like Ling et al. Did in this JFN paper. Okay, I really, really like this one. I'm going to link to this paper and also to kind of the papers that they were based on in the comments. Okay, good. So we've talked about how patterns exist. You can use these to get low order models of kind of the dominant coherent structures without resolving all of the teeny tiny physics, but that was still for very turbulent problems. So now I'm going to talk about how do you actually get reduced order models if your system is relatively simple in the first place. And so I'm going to work with this flow past a cylinder, this Reynolds number 100 flow. This is kind of our starting point in a lot of these dynamical systems analyses. And what Bernd Nowak and colleagues showed in 2003 was that if you measure the system in the right way, if you pull out the right features from this data, these modes, these three modes, two principal components and something he calls the shift mode, then you can essentially represent this complex system in a very simple three-dimensional coordinate system given by these three modes. And when you represent your system in those three coordinates, you get a really beautiful and simple description of the flow physics. In this case, there is a slow manifold where the dynamics usually live, and vortex shedding is given by this limit cycle up here at the top of that slow manifold. And they were able to derive a very simple reduced order model set of equations for the dynamics in these coordinates. This is a tour de force of dynamical systems modeling and data-driven modeling of fluid systems from a while ago. And now we're increasingly able to do some of this with machine learning. So I think that's really exciting. So instead of kind of writing down how the Navier-Stokes equation act in those coordinates to derive this model, it's now possible to just collect measurement data. And through collecting measurement data of those x, y, and z coordinates in time, we're able to essentially build nonlinear models for how those derivatives behave, how x dot, y dot, and z dot behave, as a sparse linear combination of candidate terms that could be used to describe the dynamics. Okay, so this is super simple. You take your system, you trust Bernd Nowak that you should measure this in POD1, POD2, and the shift mode. That gives you time series for x, y, and z. And then you try to model x dot, y dot, and z dot as some sparse combination of terms like x or x squareds or xy's or y squareds, a sparse combination of terms in a library. And by doing this sparse regression, we call this the sparse identification of nonlinear dynamics, you get a model that has only the active terms that are needed to describe the data. So it remains interpretable and generalizable, which is what we want for machine learning models, especially for engineering systems where you might need to generalize to new scenarios you haven't seen before, or where you might need to communicate or explain the model and control decisions you're making. Okay, so this is the SINDY method, and it can reconstruct this, this behavior. And essentially what you can see is this is actually those coordinates on the actual data. This is the full simulation plotted in those three coordinates, x, y, and z. And this is what the SINDY identified model looks like. So it captures the slow manifold, it captures kind of the separation of timescales and everything in this model. Now, after writing this original paper, shortly after Jean-Christophe Loiseau contacted me, and we started working together to make this method a lot better. And so I want to tell you about some of what JC has done, because again, I think this is the absolute spirit of how we should be using machine learning for fluid systems, or for engineering systems in general. So what JC did, and this made a huge impact in our ability to model these systems, is he incorporated two key innovations to this modeling framework. The first one is that he showed how you can enforce known physics or known constraints. And so, you know, when we were modeling this, we were doing it very naively. We just collected the data, built the library, and did a regression to find which terms were active. But we've known for a long time, well, first of all, we know that these incompressible fluids conserve energy. That's just part of the physics. But more than that, we know how that manifests itself in the equations of motion. We know that there is this skew symmetry in the equations of motion, in the quadratic terms of the Navier-Stokes equation, that kind of manifests itself as energy conservation. And so JC showed that you could enforce this constraint in the SINDY regression so that every model you get by construction was guaranteed to conserve energy. And that's huge. That means that out of this massive space of models where most of them are bad, we've already limited ourselves to a very specific family of models that are energy conserving by construction. That's huge. The second innovation, and I really, really like this one too, is including higher order nonlinearities. So the original SINDY model for the flow past a cylinder used quadratic terms because the Navier-Stokes equations has quadratic terms, because Barron's model has quadratic terms. But if you allow yourself to have higher order terms, third order, fifth order, seventh, cubic, quintic, septic, even nonic terms, then what you get is a more accurate model at lower order. And so essentially you're accounting for all of the energy that you're truncating in your POD expansion or in your principal components. You truncate your principal component analysis at just the first two PCA modes or POD modes. And then the effect of all of those modes that you truncated manifest themselves as these cubic, quintic, nonic terms. And so that's really cool. And that gives us much better models. So that was a huge innovation that JC brought into this. And since then, we've looked at several flow systems, both the cylinder, flow past a cavity. JC's looked at a lot of other flows too. And in these systems, what we're seeing here, this is just a comparison of how this model works. In this model here for flow past a cylinder and for the cavity flow, the y-axis is kind of a proxy for drag in this case. And the white curve here is what your full high fidelity simulation, the actual flow simulation, has this kind of drag profile in white. And in yellow and blue are the classic models. The classic POD Galerkin models that everyone's been using for decades are these yellow and blue. And they get the right kind of features, but they have some pretty big errors. But when you do this cubic constrained SINDY algorithm, you get much, much better agreement with the actual trends in the data. So we have less overshoot, we have the right rise time, and things like that. And what's also really nice about this that JC has shown is because you get a sparse model, a parsimonious or simple model, you can manipulate the terms and actually simplify it into something that's very intuitive for a human. And so this is the model he wrote down for flow past a cylinder. And to date, to my knowledge, this is the most accurate, most efficient, and simplest model for flow past a cylinder in the literature. This is a simple spring mass damper with a nonlinear damping term. So this is basically saying that the cylinder flow acts like a van der Pol oscillator. Really, really cool. And it's more accurate than actually taking the Navier-Stokes equations and projecting them onto POD modes. So that's really cool. And since then, working with JC and with Barrett and Nowak, we've been able to show that you can also develop these models without having access to the full flow field, without having full flow measurements. Even if you just had lift and drag measurements, in this case on these three cylinders, you can still build very, very accurate SINDY models kind of in these lift and drag coordinates. So this gives us some hope that we can actually use this for control in the real world, because we don't need access to the full measurements to have these models work. So really cool. I'm a huge fan of kind of sparse modeling in general, but there's been a ton of success on this in fluid mechanics. Now I'll point out that you can also use deep learning to get better coordinate representations. We still built all of this on POD or principal components. And with these deep autoencoders, you can get enhanced coordinate embeddings or better coordinate systems that go beyond kind of those linear algebra techniques that we've been using for the last 50 years. And so this is some great work by Kathleen Champion, Bethany Lush, Nathan Kutz, and myself, where essentially we take this autoencoder idea and combine it with those sparse SINDY models in the middle layer. So you might have some high dimensional flow data, and the idea is you build an autoencoder to learn nonlinear coordinates in the middle where it's simple. So maybe you go from 1,000,000 degrees of freedom down to 4 or 5 variables you care about, in this case 3. And then you simultaneously add this SINDY loss function so that you get a sparse, interpretable, nonlinear model on those latent variables. I think this is a really exciting idea for flow field analysis and for modeling really complex fluid flows. So I encourage you to check this out. There's also great work by Bethany Lush developing these autoencoders that instead of having sparse nonlinear models in the middle, have actual linear models in the middle. And this is closely related to Koopman theory and kind of a nonlinear dynamic mode decomposition. And I'll point out that there are dozens of groups working on this. This is probably less than half of the papers that are out on this topic now, but really vibrant field trying to find these coordinate systems where your dynamics are simple. Okay, especially important for fluid dynamics. Good. So why do we care about modeling? Why do we spend so much effort building these models? Well, oftentimes we want to control our system. So this is just one of my favorite diagrams from a paper that Bernd Nowak and I wrote a while ago on flow control. And it just shows kind of the richness of applications of control theory. And this is a recent paper by Katharina Beeker and Sebastian Peitz, which basically uses a deep learning model of the fluid flow as a surrogate that they can then use with a model predictive controller. Okay, so the idea here is that you have a complex flow system and you're going to be controlling it to try to manipulate its behavior. And what you'd like to do is run a forward simulation of the actual equations of motion, of the Navier-Stokes equations. You'd like to run this forecast forward to see if your control is doing the right thing in the future, if it will be doing the right thing. But this is far too expensive to run in real time, especially many, many trajectories for your control system. So instead, what they do is they build this surrogate model using a deep learning algorithm. You could also use SINDY or DMD or anything else to get this surrogate model. And then you use that surrogate model, which is much, much faster and still pretty accurate, and you can use it for control. Okay? So they've applied this to the single cylinder and to the 3-cylinder configuration where you get to rotate these cylinders and you're trying to control like the lift and drag on all of these cylinders. So that's the configuration here. They get to independently rotate these 3 cylinders, and they're trying to track a reference lift for the light blue, the yellow, and the dark blue cylinders. So these 3 different lift values. And when you turn on this deep model predictive controller, it starts off not tracking those, and very rapidly the controller is able to get pretty close to the reference lift. Now, this required a lot of training data. You had to take the system and push on the variables and push on the control inputs and measure what happened for a long time to build this deep learning model. But once you have that expensive offline calculation, forever in the future, it's fast and efficient and accurate. Okay, and I'll point out that this deep learning model is only using measurements of the lift and drag on these cylinders. It's not measuring full flow field information, maybe even just lift information. And what's kind of cool is if you develop a controller based on a model, like you run the simulation and you develop a controller, your model is a model of kind of that cylinder in the uncontrolled scenario. And when you turn on the control, you're driving your system to a state that it very rarely sees. This is not a normal flow state down here. And so your model is actually less valid down here than it was when you turned on your controller. And so what you can do is you can retrain your model predictive control surrogate model as you start to use it and you drive your system to a new flow state. You can retrain that model and you actually get better and better and better performance. This is much better performance, it's more accurate, and it's cheaper in terms of the control cost. So I really like this paper. I think this is pretty exciting. There's also this great paper by Ulrike Kaiser that points out, she does a comparison of using model predictive control based on DMD models, sparse SINDY models, and neural network models. And she shows that in general, if you can represent your system with DMD or SINDY, you get better control performance. But I think the real hero of this is that even for chaotic systems, which shouldn't be described by a linear DMD model, you get this very, very good, fast convergence of your control optimization. You can learn this model on the fly with about 10 data points and then turn your controller on. So it's extremely efficient to train these DMD models and to use them for model predictive control. Huge, huge point here. If you're doing flow control with model predictive control, please start by using a DMD model or a SINDY model. And if those don't work, definitely use a deep learning model. But it's really always a good idea to start with a simple model that's easy to train, fast with little amounts of data, rather than a big, beefy neural network model. I'll also point out there's a huge and growing effort to use reinforcement learning in flow control problems. This is very much bio-inspired, so a lot of these papers are using reinforcement learning for fish swimming or for perching or for landing UAVs. This is one of my favorite papers by Verma, Novati, and Koumoutsakis from PNAS in 2018, where they use a deep reinforcement learning control algorithm to learn how one fish would learn to tail another fish, kind of energy efficient kind of boat tailing. And this is a really hard problem, actually. You should go read this paper. It's excellent. It's a really hard problem. The computations alone are incredibly impressive. This is a full 3D simulation of two fish swimming with all of the resolved vorticity. And because reinforcement learning requires a lot of training of different actions, they had to run many of these simulations. So this is a tour de force in computation, but also in learning for control. So really great paper. Reinforcement learning is becoming a big part of modern flow control with machine learning. Okay, so I always want to point out at this point, I think this is a nice segue, that we really take a lot of inspiration from biology in these systems. We are deeply inspired by the control performance of flying birds and bats and insects and swimming fish. They are able to expertly manipulate and interact with a complex flow environment with relatively few measurements, without the equations of motion. This eagle can fly on an empty stomach, on a full stomach, in rain, after having injuries. It's really incredible. Insects are especially incredible because they don't have nearly the same sophistication of a nervous system as a bird, yet these insects are also able to interact with very complex gust fields. So they're able to, track odor plumes in a turbulent plume. They're able to respond very rapidly to gusts that would otherwise knock them off course. They're able to figure out from strain-sensitive neurons in their wings what control decisions to make ultra fast. And so we're just still learning so much from these systems. And again, this fits in very naturally to machine learning and modeling, prediction, control. You don't have to model everything. We don't care about all of the degrees of freedom of your fluid. At least I don't think the moth or the eagle do. They probably care about big, dominant, coherent structures that affect their daily lives, okay? So I want to end here, and I just want to kind of tell you that this is still a really rapidly growing field. So tons of opportunities for an entire career in machine learning, for fluid dynamics, for modeling, predicting, estimating, and controlling these. And progress made here will make a huge difference in technology, societal impact, industrial impact. But we also have a lot to learn in machine learning from advancing these methods on real physical systems where we know F equals ma, we know conservation laws. So really exciting field. Thank you for tuning in.